So, today we're going to talk about one of the most mind bending engineering projects happening on the entire planet. We're building a second internet, a parallel one, not to replace the one we use every day, but to run right alongside it, operating under a completely different and, frankly, much weirder set of physical laws. This is the story of the quantum internet. And that's really the first question you've got to ask, right? Our internet is a modern miracle. I mean, it can stream 4K video to your phone while you're on a moving train. It connects billions of us. So why on earth would we go through the massive headache of building an entirely new one from scratch? Well, the answer has everything to do with some rules that you just can't break. You see, to get why we need a new network, we first have to dive into the bizarre, super fragile, and totally rigid rules of the quantum world. And these aren't just technical guidelines or best practices. Nope. These are fundamental laws of the universe. Laws our current internet breaks constantly, and on purpose. It all comes down to the basic building blocks. A classical bit, the foundation of all our computers, is basically just a light switch. It's either on or off, 0 or 1. It's tough, it's reliable, and you can copy it a trillion times without any issues. A quantum bit or qubit? Well, that's a whole different animal. It's more like a soap bubble. It exists in this ghostly state called superposition, where it's both 0 and 1 at the same time. And here's the kicker. The second you try to look at it, the bubble pops. The superposition collapses, and your precious information gets scrambled. This incredible fragility is actually a law of physics. It's called the no-cloning theorem, and it's one of the most important rules in this whole game. It says you simply cannot, it's impossible, to make a perfect copy of an unknown quantum state. Full stop. And that one single rule completely shatters the foundation of how our modern internet works. So think about what that means. Right now, when an email or a video gets to a router, that router copies the data into its memory, reads the destination address, and then sends a brand new copy off to the next stop. Our entire internet is built on this store and forward idea. But with a qubit, you can't copy it. You can't read it without destroying it. And there are no backups. The original is the only one you'll ever have. The whole system just breaks down. And this chart really just drives the point home. The gap between these two worlds is huge. A classical signal is like a powerful fire hose of light. A quantum signal is a single, delicate photon. We can amplify classical signals easily. That's what makes the internet work over long distances. But for a quantum signal, impossible, thanks to no cloning. If a classical data packet gets lost, who cares? We just resend a copy. If a qubit gets lost, well, it's gone, for good. The tools that make our internet possible are literally poison to quantum information. Okay, so this sounds completely impossible, right? We've got this incredibly powerful but ridiculously fragile type of information that just can't survive on our current infrastructure. So what's the solution? Well, it turns out you don't fight the rules. You build a new system that embraces them with a really clever hybrid design. So what the engineers came up with is this brilliant idea called the hybrid dual plane architecture. And it's actually pretty simple when you break it down. Let each network do what it's best at. We use our good old reliable classical internet to be the brain of the operation, the traffic controller basically, to manage a totally separate, pristine quantum highway. So let's break that down. You've got two layers, or planes. The first is the classical control plane. That's just the internet you and I are using right now. Its job is to do all the dirty work, figuring out the best path, telling all the switches where to go, and timing everything down to the picosecond. Then underneath, you have the quantum data plane. This is the new part. It's a clean, all-optical fiber path with no routers, no amplifiers, just a gentle, clear road to carry that single photon from A to B. So what does this look like in action? It's kind of like a four-step dance. Step 1. A computer sends a totally normal internet message saying, hey, I need to send a qubit to Bob's computer, get ready. Step 2. The classical network acts like a railway signal operator, sending commands down the line to physically connect a clear, unbroken path of fiber optic cable. Step 3. Once the all clear is given, a single photon is fired down that quantum highway. And finally, step 4. The receiving computer sends a classical message back saying, yep, got it. See? All the hard work is done by the classical internet, just to pave the way for one precious little qubit. All right, so that hybrid model solves the routing problem, but that opens up a whole new can of worms. If you can't have amplifiers, that single photon is just going to fizzle out after about 100 kilometers or so in the fiber. So how in the world do you get a quantum signal across the country, let alone across an ocean? This is the next massive hurdle. You know, the fiber optic cables under the Atlantic have amplifiers built into them every 40 to 80 kilometers to boost the signal. But we already know those are just cloning machines, which means they're totally forbidden here. The quantum signal would just die. So to go the distance, we need a totally new piece of hardware, something that doesn't amplify, but connects in a much weirder way. And this is where the quantum repeater comes in. Now, it operates on a principle that is just completely different from a classical repeater. A classical one is simple. It hears a faint signal and shouts a louder copy. But a quantum repeater, oh, it does something that sounds like it's straight out of science fiction. It doesn't touch the original signal at all. Instead, it performs a kind of quantum magic trick called entanglement swapping. So what is this magic? Okay, stick with me here. Imagine Alice wants to connect with Bob, but they're too far apart. Instead of trying to send one particle the whole way, Alice creates an entangled link with a repeater in the middle. At the same time, Bob creates an entangled link with that same repeater, so now you have two short, separate links. Now, here's the crazy part. The repeater takes its two entangled particles, one from Alice, one from Bob, and performs a special measurement on them. The instant it does that, the two short links are destroyed, and a brand new, direct, long-distance entangled link is created between Alice and Bob. It swaps the connection, creating a link between 2 points that never actually sent a particle between them. It's mind-bending, I know. Now, this tech is so wild that it's being rolled out in stages. The first-generation repeaters that exist in labs today are pretty slow. They basically have to keep checking their work and trying again. The next generation will use something called quantum error correction to be way faster. And then way down the line, we'll get the third generation, which will give us the true, fault-tolerant quantum internet. But yeah, we're definitely at the very beginning of that road. So, after all that brain-melting physics, what's the bottom line? Where does this all stand today? Because this isn't just stuff on a whiteboard anymore. Let's look at the actual projects being built. And while we're at it, let's bust a few common myths about what this new internet is actually for. This is happening right now, for real. In the US, you've got the Chicago Quantum Exchange, with a 124-mile test loop running right through the city suburbs. Out in New York, Stony Brook and Brookhaven National Lab are pushing the limits on their own 140-kilometer network. And over in the Netherlands, researchers at TU Delft have already built the world's first functioning proof-of-concept quantum repeater link. The tech is officially leaving the laboratory. Okay, so that talk about instantaneous connections from entanglement swapping brings us to our first big myth. Does the quantum internet mean we can finally have faster-than-light communication? The answer is a big, fat nope. Physics is a real killjoy here with something called the no communication theorem. While the quantum link itself is instant, the actual useful information is scrambled. To make any sense of it, you have to send a classical key over the normal internet, and that key can only travel at, you guessed it, the speed of light. So no Star Trek communicators just yet. All right, what about myth number 2? The idea that this is going to be a super fast replacement for our current internet, making fiber optics and 5G look ancient. Is that the plan? Not even close. In fact, and this is maybe the most important takeaway, the quantum internet is incredibly slow. We're talking about kilobits per second, not gigabits. You will never, ever stream Netflix on the quantum internet. Its value isn't speed. Its value is doing a handful of very special things that are completely impossible for our classical internet. So what are those impossible tasks? Well, for starters, creating truly unhackable communication with security guaranteed by the laws of physics themselves. Another huge one is linking quantum computers together across the planet to create one giant global quantum supercomputer. It will also let us build networks of sensors with unimaginable precision. Think telescopes that can see planets and other star systems, or medical scanners that spot diseases years earlier. And then there's wild stuff like blind quantum computing, where you can run a program on a server that literally cannot see the data it's crunching. So, in the end, that's what this is all about. We're building this second internet not for more bandwidth, but for entirely new abilities. It's not going to bring you the next summer blockbuster, but it might bring us unbreachable security, unthinkable computing power, and a whole new way of looking at the universe. It's a specialized tool for a new kind of world. And the most exciting part is the question we can't answer yet. What will we build with it?